Hello everyone, welcome to my master's thesis presentation. So this is Suraj and today we are going to go through my thesis which is titled LearnFCA, which is a fuzzy FCA and probability based approach for learning and classification problems. So this work was done as part of a master's thesis at School of Computing at University of Nebraska Lincoln. So let's get started. So here is the presentation outline which we are going to cover in the next 1 hour or so. So first we will start with a very basic of formal concept analysis just to set a context of what it is and to basically make the later part of the presentation make more sense. Then we will see my thesis, basically what was the motivation behind the thesis, why we chose this particular problem, and what were the objectives we decided, and the contribution that we are making to the computer science research. Then we will move on to extensions of FCA or generalizations of FCA, which we explored as part of these thesis work. We won't go through each of them, but very important ones that were useful for us to study. Then we will see machine learning and FCA, which means the intersection of machine learning and FCA, where FCA has been used for learning and classification or and machine learning. And then we will go ahead and see our work, which is LearnFCA, the model that we present and how we implement it. We'll go through it in depth, the various algorithms, and then we will also see the various experiments which we did on various data sets and the outcomes. Finally, we will end with the acknowledgements and some questions and also some references. So let's get started first with the basics of formal concept analysis. So formal concept analysis is a principled data analysis technique. So basically a technique wherein data is analyzed and then organized to find relationships between various objects that are described through attributes. So this is done using a concept hierarchy, the roots of which lie in the mathematical theory of complete lattices and ordered sets, which was actually originally founded by Ville 1981. So in normal FCA, what we have is we have a set of objects and a set of attributes. Objects are represented as G, attributes are represented as M, and there is a relationship between these. So which means a particular object may have a set of attributes, or it may also not have, depends on it. And you can see here is a two-dimensional data in figure 1 which shows a bunch of objects, which is nothing but the undergraduate majors, computer science, software engineering, and so on. And at the top, which is attributes, which are prerequisite courses for each major. And so the way to interpret this data is, let's say we take a computer science as an object. So the prerequisites for computer science are algorithm analysis, computer architecture, programming concepts, discrete math, and cryptography. So one thing to note here is there may be some objects which share some attributes with objects, and there may be some attributes which share, some objects. So each of these relationship is indicated by a cross in the matrix. So this matrix is also called as a formal concept and formally represented as GMI. G is objects, M is attributes, and I is the relationship. And sometimes we also call it as a crisp FCA, or the original version of FCA, wherein the relationship between objects and attributes are complete. So formal concept analysis has a lot of applications in variety of fields, including data mining, text mining, machine learning, ontology, software engineering, and even history, sociology, chemistry, and biology. So let's move on to the next important item, which is a concept lattice. And before we understand concept lattice, we need to understand what a formal concept is. So if you remember the 2D matrix which we saw, or the context that we saw, if we find a pair A, B, where A is a set of objects and B is a set of attributes, in such a way that all the objects in A have all the set of attributes in B, and similarly all the attributes in B are belonged by a set of attributes in A, then such a pair is called as a formal concept. And when we find all these pairs and organize it using a partial order, we can actually organize it in using a line diagram, as we can see on the right side in figure 2, and then draw lines between each of the objects using a hierarchy. We call it as a formal concept lattice, and this is a very interesting diagram, wherein from which we can actually interpret a lot of important information. So these nodes are actually arranged in a sub-super relationships in the hierarchy, and each of these nodes, as you can see, are called as concepts. So if we take a particular concept here from the bottom, let's say we take mathematics. So mathematics was an object. So we can find the prerequisites of this course by navigating through the line and then see. So if we move from the node mathematics to the up, we will see that calculus 2 is a prerequisite. Intro to stats is also a prerequisite. Similarly, algorithm analysis and programming concepts is also a prerequisite for the subject mathematics, and even discrete math. So this line indicates that. Similarly, from the top, if we see computer architecture, so an attribute computer architecture is a prerequisite for, we navigate through the line. So we'll see it is a prerequisite for computer engineering and electrical engineering. And on the other side, there's also a line from there to computer science. So there are three objects or three courses that for which computer architecture is a prerequisite for. So moving on, so this is basically this. Here we see the various lattice generation algorithms that exist. I don't have the research till the latest day, but this is some important data that we have. So the original naive algorithm for generation of lattice takes exponential, which is 2 to the power n or 2 to the power m, where n is the set of objects, m is the set of attributes. And then we have the next closure algorithm, which is better than that, and that is order of nm square or mn square. The big breakthrough was done, which is an add intent algorithm, which we have also used in our project or in our LearnFCA to actually improve the generation of lattice. So that is order ln square max m, where L is the number of nodes in the generated lattice and max m is at most attributes possessed by any object. Similarly, there is also an improved add intent algorithm which improves this complexity by a little bit more. But I would say the takeaway for us here was basically its order of n cube or m cube. So it basically cubic of the number of attributes or the objects is what was the takeaway for us or for us. So now let's move on to the motivation for this thesis work. So a formal concept analysis has been introduced from very long back, but its usage in data mining has only been investigated recently, mostly in 2010s. And one of the major reasons is because of the complexity of generation of lattice. So that actually that's one of the reasons why FCA is not being much used in data mining or machine learning as such. And FCA in machine learning and classification problems has only recently been used, and there is a lot of scope in this direction, which actually can be done. So that was one important motivation for us. And there was also missing organized literature for various generalizations of FCA, which we will see later. Also for applications of FCA in various domains. And also one of our need, or one of our item, was to investigate and actually find new techniques so that we can apply FCA in various new domains, especially with advent of big data, where the amount of data is huge. And whether we can, our idea was to explore and find whether we can use FCA to find any new techniques in this direction. So here is the objectives that we did as part of this work. So first, which is part one, where we did a survey of formal concept analysis and its various generalizations, which means extensions of FCA, with some examples as well, to understand if we can reuse any of it in our machine learning work. Second part is basically to study and present a state of art of FCA applications in various fields, and specifically with an emphasis to learning and classification, because that's where we did, or we applied our FCA. Then part 3, which is our work, which is basically to propose, develop, and evaluate a new classification model, LearnFCA, to learning and classifying data. So we won't cover part 2 as such, because I think I would link my master's thesis presentation in the description, so you can go ahead and look at it. But as such, we won't cover in detail about the FCA applications, which is part 2. So let's get started with part 1, generalization of FCA. So to start with, actually, before even we go to the various generalizations of FCA, let's see how we can handle how real data with FCA is handled, because real data essentially does not have a format which we saw in a context wherein each attribute and objects are related in a binary relationship. So hence we need to apply a certain process to the real data so that we can apply FCA on it. So the first approach, which is very, very widely used, is conceptual scaling, wherein we actually transform the real world or multi-valued data to single valued data, which we can directly use in formal concept. So an example of this is, you can see it here. Now here we have data of various creatures: cat, bat, salamander, eagle, and guppy. And then we have various attributes: body temperature, gives birth, four-legged, and hibernates. Yes or no. So this is still a very simple form of real data. Real data can be even much more complex. So one way is to just scale the data. So which means we just scale the number of attributes from 4 to 8 by choosing, or by choosing every value of the attribute that is possible. In this case, let's say body temperature can be warm or cold, so we divide the attributes to BT cold and BT warm, and this way we can scale all the attributes, and we get a modified context. And if you notice, what is happening here is the set of attributes actually increases. So now scaling can also be of various types. Important ones are nominal scaling, which we saw just now, wherein basically just every attribute and every possible value of the attribute we take and then we scale the context. But there can be other data, which is an example in figure 4 here. We can see wherein there are 4 students and there are age and marks, and we are really interested in dividing or seeing if students to find which students are less than 15 and greater than 15, and similarly students who have scored greater than 45. So this way we can scale in a way as a less than 15 and m greater than 45, and this is basically an example of ordinal scaling. So where basically data can be ordered data can be scaled. Similarly, there are other options like interordinal scaling, wherein data is divided into a set of attributes, or biordinal scaling, wherein data is basically partitioned into two scales. So we won't go into more detail into all these, but as such, conceptual scaling is a very important concept which we also use in our work. So the next important one is context reduction, because the context, as we already saw, creating a concept lattice can be very costly for us. So one of the important way of reducing the context is basically combining multiple objects which share the same set of attributes, and then generating the lattice. And this way, if we notice, the lattice structure does not change. So an example is here where computer engineering and electrical engineering we can combine, and if we generate the lattice is the structure wise similar to what was originally there. Another important concept is the nested line diagrams, which is very important way, because it can partition the context into subcontext and sublattices. So an example is here. So this is a planet lattice taken from an example paper, and we can see the lattice that actually corresponds to the original context, and this can be decomposed mm, into a interesting set of lattices, which is the reduced lattice. So this is the original so this is the reduced lattice from the original context, and the nested lattice, so which basically is the decomposition that we applied on the original lattice. So this way the lattice sizes become smaller, and it can be easier for us to interpret and derive meaningful information. The third important concept, which is a lot applicable in big data, wherein a lot of noises are present in the data, which means false positives are present, is iceberging, wherein actually concepts with low extent size are just removed. So this way, a good amount of concepts can be removed and the lattice size can be smaller. So here is an example of the iceberg lattice. So this is from a modified UCI machine learning zoo dataset. As you can see, how the concept lattice looks like, but if we reduce it by applying iceberging, which means removing concepts wherein the concepts only cover half the object set, the lattice now becomes very nicely structured, as we can see on the right side. So that's about iceberging. Now there's also another way of iceberging or noise removal, is for every concept we could define a stability measure based on certain factor, maybe the objects or attributes, and then we can just ignore or remove concepts below a certain threshold, similar to iceberging, but just the concept stability measure can now vary based on domain to domain or situation. So cool. So these were the important ways of handling real data. So now let's get started. Let's move on to various extensions or generalizations of FCA that we explored and we thought were important. So no doubt first and very widely used is the fuzzy FCA. Fuzzy FCA is based on crisp FCA, which we saw earlier, and fuzzy set theory. So fuzzy set theory says that an object and attribute may not have a complete relationship, and there could be a varied degree of membership between objects and attributes. So this actually extends the original FCA from GMI to GMI mu and eta, where mu is a number between 0 to 1, saying the degree of membership between an object G and attribute M, and chi is a confidence threshold, which basically is used to convert it to crisp FCA, or a threshold which can be used to remove certain objects where the relationship between objects and attributes is very less. So this becomes very useful in applications, in real-time applications where relationships are incomplete. And here is an example. So we have a bunch of objects here, G1 to G6 and M1 to M6. And the relationship now says G1 is 0.5. So point belongs to M1, or M1 belongs to G1 with 0.5, and similarly, and so on. And if we actually apply the confidence threshold chi, which is 0.5, we can easily scale this to a very to the crisp FCA, which looks like this. So where G1 belongs to M1 and G2 belongs to M2, and so on. So anything below 0.5 is discarded. Anything greater than 0.5 or equal to 0.5 means that the attribute belongs to the object. So next, moving on to rough FCA. Now rough FCA is again the original crisp FCA which we saw, and adding to it is a rough set theory. So rough set theory basically says that certain set of objects can be approximated by a lower and a higher bound. So this is very useful where in certain set of objects cannot be uniquely represented by a given attribute set. So the idea comes from here, as we can see in figure 3, we have a continuous curve which is now drawn on this graph. But since we cannot approximate a continuous curve, we can approximate using a lower approximation, which is the blue line here, and the higher approximation or the upper approximation, which is the red line over there. So that's the overall idea. So basically a set P has now a P lower bound and a P upper bound sets, using which the set P is uniquely represented. So as such, we can say now using rough set theory, rough FCA can be represented as a K, which is GMI, the original crisp FCA, and an approximation P that can be applied to the set of objects. So this is also an important extension which is used in large and complex data. And so here is an example. We can see, let's say we have this context of 7 objects and 6 attributes, which if we notice can be partitioned into G1, G2, G4, G3, G6, G7, and then G5, 4 sets. If we draw the lattice structure, or if we just notice, we will see that these attributes and objects share. These objects share basically have the same set of attributes. G3, G6, G7 will form a concept. G2, G4 will form a concept. Let's say, but then if we have a requirement X wherein we want to actually represent G2, G3, G4 and G5, so which means G3 has to be included, but G6, G7 we don't want to include. Now notice G3, G6, G7 is indiscernible as such in the context, which means the attribute that they have is same. But then now we need to only represent G2, G3, G4, G5, excluding G6 and G7. So this sort of problem can be handled using a lower bound of x and a higher bound of x, where in P lower x basically includes the set of concepts or the set of objects wherein we exclude G3, and P higher we include all the objects that are part of that set, which means G3, G6, G7 are excluded. That's the overall idea. So which means x is now represented by P lower x and P higher x. And this way, if we draw the formal context, we will get two different context here, the lower approximation context and the higher approximation context. So we also say the boundary region, which is P higher x minus P lower x, G3, G6, G7, and we can also define an accuracy for error of FCA as P lower x by P higher x. And if you notice, if basically this one accuracy is 1 if we have P lower x and P higher x as same. So if we see, or if we draw the concept lattice and of the original context, we can see that these lower sets and the higher sets can be represented as two different concepts, the lower one being G2, G4, and the higher one wherein basically the which is G2, G4, G3, G6, and G7. So in one case G3, G6, G7 is excluded, and in the other one it's included. So the idea is the original set lies somewhere in between these two. So next, moving on to monotone FCA. So it is a crisp FCA plus Boolean monotone formulas. So this was developed at UNL by Dr. Deogan and his student Saquer in 2004. So the whole idea here is to define a monotone formula wherein which is a disjunction of conjunctive expressions on the attribute set. So basically the attribute set is now extended to certain additional possibilities, and then we can generalize the whole context by allowing monotone formulas in the intent and set union for extents. So in such a case, the monotone context is actually an extension of original GMI to GM and italic I, where M is the space of all monotone formulas that can be generated from M. So in the original paper, also what is defined is a feasibility of monotone formula. So which means if the attribute set or the extension of attribute set can actually be a concept, and there are also some order theoretic properties that are proved there, which actually says proves that it is an FCA or an extension of FCA, and this extension is allows actually to represent knowledge in information retrieval system, and so that there can be queries that can be made onto it. So here is an example of it. So let's say we have a FCA context with 6 objects and 5 attributes. We can define two Boolean formulas B1 and B2. So B1 is M3, M4, M5, basically the intersections of M3, M4, M5. And B2 is intersection of M1, M2, M3, M4. So these can be two Boolean conjunctive expressions of attributes representing a particular scenario, and we can say a monotone formula which is B1 union B2 or a disjunction of B1 at B2. So if we actually see, we also say F1 is a feasible monotone formula because both B1 and B2 are feasible intents. So which means if we draw the concept lattice, then we will see B1 and B2 both are concepts, and hence the union of it, which is a monotone formula F1, is also is a feasible monotone formula. So the lattice looks like this, so where we can see G1 actually belongs to B1 and G2, G3 belongs to B2. So the next one is probabilistic FCA. As one can guess, it's FCA plus probability theory. So there are a few generalizations that actually exist in that have been used in literature or in various works. And most important one is basically extending the traditional binary relationship. So basically the whole relationship is now extended to a set of worlds W, and each world having a probability of existence. So the probabilistic FCA can be defined as G, M, W, I, and P, where W is a set of worlds and P is a probability measure on each of these worlds. So here is an example where we have probabilistic FCA. So where the probability of each world W1, W2, W3 is 1 by 2, 1 by 4, and 5 by 12. And G1, G, and M, the relationship between it can vary in each of these worlds. So as we can guess, this can be very easily scaled to crisp FCA by combining objects, by defining complex objects, which is a combination of objects and worlds. So next is temporal FCA, which is basically integration of temporal phenomenon into crisp FCA, which means adding a notion of state or time to each of the objects or to the attributes. So there are a few generalizations for this exist. And the important ones being in figure 13, the first one we can see where time points itself are used as objects. So which means we have various times and various observations M1, M2, M3. And another one which is TCSS in figure 9.2, where each object at a particular time can be defined as an object, and then various observations or various attribute values could be present. And this is also further generalized to temporal fuzzy FCA, where the values of or the relationship can be now incomplete or vary between 0 and 1. So the main idea here is it allows us to visualize objects or evolution of objects in the lattice. So we can have various lattice at different points of time, and we can track how the object property changed from one time to the other timestamp. So next is logical concept analysis. Basically, this is similar to the monotone FCA that we saw. It's just that the attribute set is now, extended to include all various possible combination of logical expressions. So in this case, what happens is the set of attribute M is now scaled to 2 to the power M, where 2 to the power M is the power set of attribute M. So an example is here wherein we have 4 objects and there is a description A, B, and we can now have all possible combination of attributes, that is A or B, A and B, and so on. And each of this values can now be scaled to get our scaled FCA context. So the next one is relational concept analysis. So this has its root from relational data sets or relational data. So wherein basically the concept of RDBMS is integrated with FCA, and hence it's mostly used for integrating or representing complex relational data. So here is an example. Let's say we have a student table and a course table, and then student has ID, name, phone as attributes. Course has name, number, and credit hours, and there is a relationship and that student enrolls in the course. So each of this can now be extended by defining a collection of contexts and intercontext relationships. So basically this ends up in giving us a family of lattices and a family of concepts. So that's why here there is a set of context Ki, and there is a set of objects Gi, Mi, and Li. And R is a set of relationship between Ri is a set of relationship between Gi and Gj. So each of these attributes can be scaled. So which means the student table here can be scaled as a relationship between ID name, ID phone, and so on. So each of this will be a context. Similarly with course, and then the relationship enrolls, which is between ID and number, student ID and course number, also yields another context. So basically a family of contexts are there. And the authors have actually integrated this concept into a famous Galicia tool, which is very popular for data mining. So those were the important extensions. So other generalizations that are not so important, but we thought we should mention it here, is triadic FCA. Now here also, here basically this adds another new dimension to the FCA. It's not just objects attributes, it's now objects attributes and conditions. And then the authors also prove various order theoretic, graph theoretic results to show that it is similar to the original FCA. The other important generalization is the pattern structures, which started, which started mostly from 2009, wherein the author defined something called as pattern structures, which can be used on graphs and numeric intervals. And the authors claim that these can be efficiently computed and visualized, and similar to the original FCA. So the last one, but not the least, is possibility theory view of FCA, wherein possibility theory, which is an alternative to probability theory, is integrated with FCA. In possibility theory, there are a set of functions and a possibility distribution, which now defines the FCA, and the authors actually say that we can use this possibility theory in certain areas like uncertain and fuzzy data. Okay, cool. So the next part of this thesis work we are going to present is the applications of FCA and its generalizations. We won't cover this in much detail, but I thought I'll just talk a bit about the various domains that we explored. Mm, so basically, we went through about 150 papers of FCA related to FCA, and for of FCA applications and approaches and its generalizations. We divided them into three categories: data analysis, knowledge management, and learning and classification. So in data analysis, basically anything to do with the analyzing of data, we categorized, and anything to deal with knowledge discovery, representation, or ontologies, we put it in knowledge management. And then the third or important one where we were more interested was the learning and classification category. So basically all the learning and classification that has been done using FCA, along with some of the important things like streaming or big data, and generating efficient models for unclassified data. So to go into detail, I would actually recommend you to look at the thesis work, wherein we present all the different papers that we went through in a tabular format. So cool. So that was all about applications of FCA. So lastly, or the third part which we are going to cover, is our work which we did as part of this thesis. So basically, we went and developed a new approach called as LearnFCA for the learning and classification problem. And let's see what we did. So firstly, let's go through what work or how FCA can be used in FCA learning, and what was done before our work started. So as we know that machine learning traditionally falls into two parts, which is supervised or unsupervised learning. So in supervised learning, the learning happens through a set of given values, or given data and classes. And unsupervised for learning, where we actually, to start with, there is nothing for us as data or as reference. So we have to learn as and when we process the data. So if we refer back to what FCA does, is from the object attribute relationship basically tries to learn and create predictable patterns. So these predictable patterns now we can use it and then store in a temporary storage or something to build our knowledge base. And this knowledge base can then be used to basically classify the data. So in short, use of FCA with various existing machine learning models and domain expertise can actually lead us to interesting results. So that was our original idea. So to start with, let's see a naive algorithm or a very basic example of how we can use FCA or the FCA lattice to classify some of the data. So let's say we have this original context which we took some time back, wherein we have a set of creatures as objects: cat, bat, salamander, eagle, and guppy. And we have body temperature, gives birth, four-legged, and hibernates. But then we also have additional information, which is the classes or which class each creature belongs to. So here we can see cat and bat are mammals, but not the others are mammals. So the whole idea here is to classify the creatures into mammal or not a mammal by just seeing the attributes. So the first step is to actually scale the attributes, which we saw using nominal scaling, wherein each attribute can now be scaled to two attributes. And we can then go ahead and create a lattice, an FCA lattice, which looks like this. And this also on the down we can see various objects: guppy, salamander, and on the top we can see the set of different attributes. The only difference you can see is each of these attributes now objects have now a plus or a minus sign, indicating plus sign means it is a mammal and minus sign means it's not a mammal. That's the additional information we included along with the object. So if you want to classify these objects, one very naive strategy we can use is to just start from the top of the lattice, which means from the infinitum of from the top concept, and then go down one by one to each of these concepts, and then use the line relationship to see if these attributes actually can partition the set of objects that we see. So which means in this case, if we see the attribute bt cold, if we go through the lines, navigate, we will see that guppy and salamander are related to bt cold, whereas bt cold is related to no other objects. So which means the attribute bt cold now partitions or can be used to derive a rule saying bt cold derives guppy and salamander, which means bt cold derives negative examples. So similarly, if we go to the next, hence we include bt cold uh, in our set of classification concepts, which we will use to derive some rules. So next, if we move ahead, similarly, if we take GB no, which is gives birth no, and we see the lines from there, we will see that they point to salamander and eagle, which is also good for us because it partitions the set of objects now, or it classifies all the negative examples. So hence we will also include that in our rules. The third one, if we notice, FLS, which is four-legged S, actually derives salamander and cat. So if we see both of them, salamander is a negative example, whereas cat is a positive example. So hence this particular concept is not of any much use to us. So we'll ignore this and then we'll move ahead similarly to the next one, which is HBS, hibernates S. If you notice, it also derives positive and negative both examples, so it is of no use to us. Similarly, if we move ahead, we will see FL no, HB no, BT warm, and GBS. And in the next layer also, if we move, similarly we will see that none of these attributes uniquely or partition the set of objects into positive or negative examples. So finally, if we move ahead, we will see that this particular concept at the end here, represented in green, actually classifies all the positive examples, and hence we will also include this in our set of rules. So that's the whole idea. So here we present our naive algorithm that we discussed just now, where we have input as a set of formal context, GMIS, and our output is a set of classification rules or the concepts wherein we can derive either all set of positive examples or all set of negative examples from the concept. So first step is to generate the list of concepts and the concept lattice. And while not objects are classified, we move down from top, move right and then down to find a concept that classifies most number of objects, but of a particular class, but not the other class. And then we keep including those concepts. And finally, from those concepts, we actually derive our classification rules. In this case, we have BT cold derives negative examples, GB no derives negative examples, and a combination of BT warm and GBS, which is the concept below, in the below layers, if you remember. So that actually derives all the positive examples. So that's how we can derive a set of rules for our input data. So that's the whole idea of the naive classification algorithm. So before we move ahead, let's just do a little bit of literature review of FCA and machine learning, starting what has been happening in the past few decades. So before 2000, if we see, there were a bunch of models that were proposed like Sherrod, Galios, Legal, and all of them basically were mostly all of them, what they did were to generate classification rules similar to what we did just now from the lattice. And then some very naive approaches of machine learning were used, like ID3 algorithm, and some heuristic techniques were used, and some other approaches like defining the most specific rules that classify the largest number of examples and so on. So between 2001 to 2010, people started actually integrating some important machine learning models into FCA, like the naive Bayes and the nearest neighbor, version spaces, or the reinforcement algorithms, uh, or even neural networks in 2007, support vector machines in 2009, or decision trees. So these were mostly that were used in combination with the concept lattice for classification. And there are some of the recent ones, which is after 2010, in the last decade, used mostly, if we notice here, is use of parallel classifiers, multi-classification, use of cloud services, and things like that, because of the advent of big data. And we had faster machines, and also some latest or important concepts of machine learning like dagging and bagging that have been used. So moving on to our work, LearnFCA. So before we go into the detail, let's see some basic definitions that we developed. The first is formal context with classes. So we just scaled the original formal concept with a set of classes. So wherein each object can belong now to one class or a set of classes. Then similarly, we extended the formal concept with classes. So wherein class or a set of classes now can be associated with the formal concept based on certain classification strategy, which we will see. We also defined a concept probability vector, which means a probability vector that we can assign to each of this concept. The idea here was for lattices with large number of nodes, using a classification strategy to define a single class or just a couple of classes or few classes can be difficult. So that's why whole we had a vector for each of wherein the values of each of these vector corresponded to all the classes, and we could have a number, a fraction of each class for a particular for all the concepts. So that's what we have. So we have a probability vector p1 to pn, where n is the set of classes, and each of these pi says how much of the particular concept belongs to that particular class. So the chance of being classified to each class. So the formal context was also now scaled to fuzzy, so which means the values, the relationship is no longer complete. So that's why we have mu, a fractional value between 0 to 1, and chi as a confidence threshold. And our classification strategy, which was defined as which was basically, it's just the fraction or ratio of objects that belong to a particular class in that particular concept. So which is nothing but the size of extent, or the number of objects for Si divided by the whole extent size. So our idea was to now classify an object O. So to classify a particular object O, we have to first go into the lattice and find a relevant concept CO that contains O, which means that contains the object and had the maximum extent size. And then from that particular concept, we can now we first find which class that particular concept belongs to, which is nothing but the maximum probability, and assign that particular class to the object O. So here is an example where we have a fuzzy FCA, 6 objects and 4 attributes, and we have 3 classes here, and we can see the fuzzy relationship or the fractional values of the objects and attributes. So let's now see that in the example. So if we actually draw the lattice or the fuzzy lattice for this particular context, we will end up in having these nine different objects, and what we can do is actually then go ahead and for each of the concepts, what we do is we use our classification strategy and then derive the probability vector, and then using those probability vector we can actually classify the objects. So this is algorithm 2. So what we do is how we start with is we have a fuzzy lattice which we already generated using fuzzy FCA, and our output is basically all the instances and their predicted classes. So first we use an instance map which is initially empty, then we go through each concept in step 2 here, fuzzy, and then for each object that is present in the object's extent, what we see is we find the extent size and we try to get the size that is present in the in the existing instance map which we have. So the whole idea is we keep updating the instance map to with the most relevant concept that we have found so far. So that's what we do here. If m is less than n, we actually then update the instance map with the at the location O with the probability vector of that particular concept. And finally, what we do is we just go through the map which we have. So which means in the map we have objects and the relevant concepts, and then we find the maximum probability that is present in the probability vector, and we assign it to each of these objects. So the result of it gives us this. So if we notice G1 here, which is object 1. The relevant concept is number 4, and if we see that the probability vector is 1 0 0, and that's why G1 is now classified as class S1. Similarly, other objects are also classified, and we notice we are able to classify 5 out of 6 concepts, 5 out of 6 objects successfully. So we have a good amount of classification accuracy here. So here is the detailed calculations. As we can see, one example is for node 6. Let's say we have extent O is G2, G3, G4, G2, G3, G5, G6, and intent is M4. So for each class, we can compute P1, P2, P3 as extent CC in S1. So which means what are the objects that belong to S1 from the extent from the concept, so which is nothing but only G1, and total extent size is 4. So that's why we have 1 by 4. Similarly, P2 is 0, P3 is 3 by 4, and we get our probability vector as 0.250 and 0.75 for node 6. So more details. So if you notice, for object G3, concepts are nodes 1, 2, 3, 5, 6. So we have actually five concepts that have object G3, but the most relevant concept was node 6 because its extent size was 4, which is the maximum one, which was our strategy, and the predicted class for node 6 was actually max PV6, which is nothing but S3. So few details on how we implemented LearnFCA. So there's a famous tool, Java based and very old tool, which is ConXP, and ConXP NG is next generation of that. So we used that, we took the source code of that, and then we added support for fuzzy FCA, classes, and concept probability vector. And we developed our tool, which was based in Java. And we used the algorithm that we saw some time back, algorithm 2. We implemented that so that we could classify the objects. We also modified in the later stages of our project. We also modified to use add intent algorithm for lattice construction, because we had a large number of objects. So that was thing. We also developed a text-based classifier, since developing a GUI-based classifier just became more clumsy where we had a large number of objects. So that's why we developed a text-based classifier. So which means we just outputted the various objects and their predicted classes, and we also added code for randomizing and selecting the training and test set, and also the capability of reporting accuracy on large data sets. So this tool can be accessible at GitHub at this location. So let me just show that real quick. So I have it open already here, as we can see. So this has the whole set of basically the whole code here that we have used as part of this project. So we can see it implements fuzzy formal concepts. We have the capability to classify objects into classes. We have incremental lattice building algorithms, which is also still in progress. There's also a branch of for ontology integration, which is out of scope of this presentation currently, and there is a detailed description on how we can run this whole tool. So that is about it. And the original tool which I was talking about is a concept explorer, is this one, which is a pretty good and pretty handy tool. So we use this Java based tool, and then we actually went ahead and enhanced it for our work. So So the next, lastly, the fuzzy lattice generation algorithm which we used for our work is presented here. So the whole idea is, if we notice, we did not need to use the fuzzy threshold of 0.5, because we went ahead and then we actually we'll see that in later next few slides, how we partitioned the data, or we scaled the data, and hence we did not need the original threshold of 0.5. So the whole idea was, now here in this algorithm, is we maintain a training map and a class map, wherein we keep updating the training map, and we initialize the probability vector of each of the concept by navigating through the lattice and seeing the total number of objects that are present in the lattice, present in the object, by checking the total count from the class map. So next, let's go through what how we actually applied the algorithm or our model to the experimental data sets. So first of all, let's see the data setup that we used. So our data that we used was the original data that we used were nothing but images. So these images were first translated into encodings using machine learning algorithms, which is deep learning algorithms, which was done as part of a separate project by Muhammad and others. So they used various deep learning techniques to derive a matrix, or to derive various instances and their features. And these instances and features were the input for our LearnFCA model. So these encodings were initially double, but we normalized it to 0 to 1, so that we can now use the fuzzy relationship. And then we also did attribute scaling, because the original set of 64 attributes were now scaled to 512 using interordinal scaling, which we will see in the next slides. And then, so that we could capture meaningful relationship from the data. So here is a description. We can see the input image here is first basically, first, deep learning techniques are applied onto the imagery to get a compressed feature space, which is nothing but a set of instances and set of features. And these were not then used in LearnFCA, or basically organized into a lattice using FC, and then were classified into various classes like C1, C2, C3, C4. So the data sets we used were MNIST, which is the well-known numbers data set, wherein number of classes are 0 to 9, 10 classes, and number of handwritten digits were the instances, which were about 60,000. Then we used the Omniglot data set, which is a very bigger data set, and where the number of classes were huge, 1623, and instances were 14,000. So the characteristic of this data set is basically there are a lot of number of classes. Lastly, the third one, which is the colon cancer data which we use from the GDC portal, wherein number of instances were 1021, and which were classified into two classes like malignant and non-malignant. So here is the data that we used first to scale the attributes. So basically the fuzzy data that we had here in the form of matrix G1, G2, G3, G4 and M1, M2, wherein the values were 0 to 1 were now scaled using interordinal scaling. So in this case, it's scaled into four. The data is being thrown into four buckets, but in our case, the original data was had 64 attributes, and each of these were scaled to to basically to n times. So that's why we have this algorithm extend features en. So wherein the feature set was now expanded to f multiplied by n. So basically the whole idea is just to throw. So let's say here g1 and m1 is 0.7, so which means this will belong to the third interval. So we have g1 and m1 3 as the relationship here. So lastly, the final algorithm which classifies the whole encodings based on the fuzzy lattice is presented here. So we can see the input is a set of encodings wherein we had I cross f, and there was f is divided into f1 plus f2. So f2 is basically classes. So in short, if we only had one class here, the last one was class, and the set instances were now divided into I1 and I2. I1 is the training instances, which means from where we learned, and I2 is the test instances which were classified. So the overall algorithm is, first is we extended features by n times, and then we use the gen fuzzy lattice to generate the fuzzy lattice, which actually generates the instance maps and the training maps, and also updates the concept probability vector for each of these concepts. And then we use the classify using lattice algorithm, which we saw, wherein we go through each of these concept to find the most relevant concept for the object, and then classify each of these objects. So these were the results on the data sets that we saw, MNIST, Omniglot, and Cancer. So cancer images. So for MNIST, we can see we first tried with binary encodings, wherein we only had basically we use the fuzzy lattice, which means the threshold as 0.5, and then we classified the objects. So in this cases, we see that our accuracy was very less, which was 25.2. But as soon as we extended our feature set and used floating encodings, we were able to achieve an accuracy of 96.4 to even 100. If you notice, we were only able to use objects 500, number of objects as 100 and 500 for our classification. So that was with MNIST. So with Omniglot also, we were only able to use about 5,000 objects because of the limitation of our model, because the FCA lattice, actually the generation of FCA lattice is complex, and hence it took a huge amount of time. But as such, even with Omniglot, we can see that with scaling of attributes, we were able to achieve an accuracy of only up to 55.4 here. So as the number of objects increased, the number of classes increased, our accuracy dropped. So that's an important observation. Lastly, with cancer images, where we only had two classes and 1,000 objects, we were able to actually classify with the classification accuracy of 98.27. So important observations as we discussed. So our model performed well or better with floating instead of binary, which is expected because we were able to capture the features more closely. So feature scaling helped us to capture more relevant features efficiently. Also, with the number of classes, as we saw, when the number of classes increased as an Omniglot dataset, classification accuracy only decreased. The dataset size, we saw that since lattice creation is by default exponential, we were not able to run more than 5,000 objects, and it actually took 2 hours for 5,000 objects to classify 5,000 objects, and we were not able to run the entire Omniglot dataset because of a lack of memory and other issues. So I think that's it. Conclusion and the future work. So as such, we did review about 150 papers related to FCA to see the various extensions of FCA that have been used. Also, we figured out that we have a bigger limitation. We have a limitation on our model for bigger data sets, and hence this could be a good amount of direction for our future work. Specifically, we could use incremental algorithms like add intent or any recent algorithms to improve the accuracy, not accuracy, to improve the efficiency of our generation of lattice and classification. Also, we can use some noise removal techniques like iceberging to remove some of the irrelevant concepts, and use some context reduction techniques like the line diagram, the nested line diagram, to see if we can reduce the lattice structure. The last direction or a different direction is use of temporal FCA, which we can use to persist and then save information over time. The whole idea from this comes from the fact that each of these images belong to a particular patient, and we can use various lattices at different points of time to see the progress of the patients over time. So next, acknowledgements. I'd really like to thank the supervisory committee for this work, specifically Dr. Dayogam, who is a primary advisor, for suggesting various research directions and working with me right from the beginning of taking courses to till the end, till now. Dr. Veriam, who also suggested me various new research directions during the course of my master's work, and Dr. Hassan, with whom I worked as a teaching assistant for quite a good amount of time. Also, my project group colleagues, specifically Adam, whose expertise from computational biology helped a lot. Mohammed, who helped who basically explored the various machine learning techniques that we used in generation of features. Then CSC department or School of Computing, which actually gave me teaching assistantship during my early part of this of my master's work. Also, trio programs who gave me assistantship during my thesis writing. So important references, I would suggest the important one is the Coursera course, which is a very basic FCA course for anybody to start with who has no knowledge from the beginning. It really goes through in detail about each of these FCA concepts that we discussed earlier. The Concept Explorer, which is the fundamental or the basic tool which we used to enhance and implement our work. An important survey paper, Polman's of 2013, which actually explores through various models and techniques. Lastly, the GDC data portal, from where we got our images, cancer images. And I think that's all. I'm open to any questions that